at the Courant Institute of New York University from 2017 to 2019, where he introduced the peer-led team learning, PLTL, for the pre-calculus course. Dr. Patel is currently working as an associate professor of instruction at the University of Texas at Dallas. I am happy to invite Dr. Jigar Patel for his valuable talk. Title of the talk is A Dynamic Contact Problem. Over to Dr. Jigar Patel.
Okay, thank you so much for arranging this talk, Professor Shah and Dr. Srimari. My talk is basically inspired from my work that I did during my PhD. So this is a very simple and practical problem. I'm going to try to explain you, the full problem in detail and associated work. All right. So I'm going to start this idea, this talk with. Okay, let's see. Okay. So these are the parts of my talk. I will start with a basic introduction, and then I will give you the problem formulation and its mathematical modeling. I will also discuss what sort of numerical technique was used. And then as a result, what we got is called linear complementarity problem, which is kind of a very popular problem. We introduce a very novel method to solve this particular problem, and the results were really impressive. This work is published in Electronic Journal of Differential Equation in 2013. So let me first tell you the motivation part, how from what inspired me to work on this particular idea. So first and foremost, if you think about any structure, you can assume that at the time when you build the structure, it is defectless, right? So pretty much the brand new structure are defect-free structure. As we use them over the time, they start developing defects, right? Think about it. What is the worst form of defect? The worst form of defect would be cracks, right? So imagine that you are traveling in a plane, right? And you notice that on one of the wing of the plane, there is a crack, right? And you immediately notify your pilot that, oh, I noticed there is a crack on the wing of the plane. And think about it. Pilot tells you like, I have noticed this crack like 1 year back and it's flying well. You don't need to worry. Would you board that plane? Answer would obviously be no, right? Because, you don't want to take any risk with the damaged structures, right? So this is just one example. Same thing is true for the bridges, buildings, and all the other things, all the other structures that we see in the real world, right? So as we use them, they start developing defects, and we need to study these defects carefully. If plane has a crack, we can't really replace the whole plane, right? So financially, it is going to be very difficult, right? So we have to find out some innovative way to find out whether or not the structure contains a defect or not, right? So that was the motivation of this particular problem. Now, obviously, I did not use aeroplane with the crack or building with the crack. Instead, I try to simplify the problem, and I try to make it as simple as possible, right? So I consider a three-dimensional cantilever beam for my study, right? And this cantilever beam, it's really basically a beam that is one end is attached to a wall, the other end is free, all right? Now, type of the defect, I consider the worst type of defect, which is crack, right? So with a structure, there are many type of defects that it may have, right? So it may have some imperfection, some bubbles in when you build the structure, right? But the worst form of defect will be the crack, right? And the material with the crack, it's really dangerous at some point, because as as you use them, sometimes this structure they vibrates, right? And when they vibrates, these cracks they propagates and they increase, right? So it is very important for us to study this particular problem, right? And that's the reason why the simplest type of structure is considered. Now we think about this issue that where should we put the crack, where the defects could occur. In general, if you think about this, you will get answer immediately that, you know, the normal part, the most usual part where you can find the cracks and defects, they are really joints and corners, right? So many researchers, they study this particular type of problem. They put the cracks at any random location, right? So far nobody did the problem where the crack is actually located at the supporting wall, which is really the corner of the cantilever beam, right? So this is one reason why we were interested in this particular problem, and it's highly nonlinear problem, pretty difficult to solve. It gives us a feeling that it's not a well posed problem, but we did the computation, so that really proves that it is a well posed problem. However, the analytic solution is completely unknown at this point. All right, so our assumption is like a very simple cantilever three-dimensional beam with a crack at the supporting wall. So here is the first picture of the beam, which is a brand new beam, three-dimensional. The dotted part represent, you know, the actual beam, where one end is glued to the supporting wall, the other end is free. As I said, this beam is called cantilever beam, right? When you apply any force on this beam, it will have some deflection, right? And this displacement field can be calculated exactly, right? So if the beam does not have any crack, analytic solution is known, numerical work can be done. This static problem certainly has a unique solution, right? So you apply load on a one of the end, or you can apply the uniform load, and you try to predict the deflection of this beam. So as I said, this problem is very well known. Analytic solution is known. What is more interesting is this situation, right, where you have a three-dimensional cantilever beam, and then as you see, there is a crack located at the supporting wall, right? Now, what is interesting here is, you know, when you apply load on, when you apply a force on any part of this beam, it is going to have a deflection, right? And if you apply the force in the opposite to the crack location, then the crack would open, right? Again, the static problem itself gives us a feeling that this is a highly nonlinear problem, computationally kind of challenging. So you can imagine that dynamic problem would be even more pain, right? So obviously what we did is we try to model this situation mathematically first for static problem, and then we add dynamics into it to get system of PDE that represent this dynamical problem. I use this numerical idea to solve this system. So let's actually go through it. So as you see in the picture itself, there are few parameters that I have used here, right? So L represent the length of the beam, H represent the height, theta represent the thickness of the beam, and that D represent the length of the fixed part of the beam, the part that is completely glued to the supporting wall, right? That really means that H minus D is the length of the crack, right? So these are the variables that we are considering. X is really a point, and U of Tx represent displacement of this three-dimensional node. with respect to the applied force, right? So here are all these parameters that I have mentioned. L represent the length, theta thickness, h height, d is the height of the fixed part from fixed part of the beam. Rho x, it's the density of the beam. It is an elastic structure, so we have to consider some elasticity related parameters to make the problem more realistic, right? So rho is the density. G of x represent elastic modulus of the beam, and this property of G of x is it's a 4x4 tensor numerically, and it has it is indeed a positive definite matrix. So all eigenvalues are positive. Computationally, the situation is simple, right? U of t comma x, this really represent displacement of node x at time t, right? So it is a displacement of node x with respect to applied force. Now, let me mention here that t represent the time, x1 represent the variable that represent the height of the beam, x2 and x3 represent the length and thickness of the beam. It is important to keep this in mind because we are going to discretize this variable, this u variable very soon. All right. So that discretization will help us doing the computation numerically. All right. Epsilon tx and sigma t comma x, they represent linearized stress and strain respectively for the space element x. Omega, this is the domain occupied by the beam. As you see, the beam itself, it has a length L, height h, and thickness theta. So 0 comma theta cross 0 comma h cross 0 comma L. This is the total domain occupied by the beam in the reference configuration. And I'm going to use symbol lambda, symbol omega, capital omega for this particular for this domain. All right, so now here is the problem formulation. The potential energy, we are going to start with something very simple and straightforward. Given some body force, when you apply a force on a free end of the beam, right, you will get some deformation field, right? So assumption is when you apply the load, beam is going to deflect and it will take some sort of a shape, right? And we are going to make some assumption on the shape based on the standard available principles. All right. So the potential energy of the beam, potential energy of the deformation field is really given by this integral equation, right? It's a half of integral over the domain, partial derivative of ui with respect to xj times g ijkl. As I said, g is a 4x4 tensor. Times partial derivative of u with respect to uk with respect to xi minus that force times ui. It's integral over the domain, right? So this is again a standard formula that represent the deflection of the beam, right? And that is considered as a potential energy for this related to the static problem. Natural state space, when where we are trying to find out our solution, is a Sobolev space, right? So Sobolev space W12 omega comma R3 is the space where we will be trying to find out the solution to this static problem, right? So we will get series of perturbed problem, and that together is going to give us, solution of this dynamical problem. So solution that we are going to look for, it is in the displacement u is restricted to a convex set J, right, by the unilateral type boundary condition. Now let me tell you what is the unilateral type boundary condition. Now think about it. You have a wall and there is a crack, right? So when the beam vibrates, what is going to happen? When the beam goes down, crack will open. When the beam goes up, the crack will close, right? Now, how the crack is going to close, that is completely unknown, right? It depends purely on applied force. If you apply more force, it doesn't really, it might happen that the crack could close in a regular way, meaning that the node near to the crack tip meets with the wall first, and then the next one, and then crack closes, beam goes up, and then it goes down, right? So this is like very normal vibration process, but every time beam goes down, the crack would open. Now think about it, why this problem is really interesting. When crack closes, many interesting thing occurs, right? This nodes that is on the crack tip, they are going to hit the wall with non-negative velocity, right? Because it is going to hit the wall with non-negative velocity, there is energy dissipation, and this energy dissipation are going to make the vibration slower, right? At some point, when you compare the normal beam vibration and the crack beam vibration, obviously crack beam vibration would stop earlier under the same applied force, right? So that is really like a very simple understanding, right? So as I said, let me tell you what is this unilateral boundary condition. Unilateral boundary condition really means, when the crack closes, we assume that no node sitting on the crack would penetrate the wall. There is no way that node is going to cross the supporting wall, right? So that is what we mean by the unilateral type boundary condition. It can go all the way up to the wall, it will hit the wall, and then it will bounce back when the beam goes down, right? So that is really unilateral boundary condition in a simple wording, right? How do we model that set? Here is how we are going to model it. I consider set S, which represent this particular situation where x2 and x3 component of node X has value 0. Value 0 means they are at the wall, right? And the x1 component could be anywhere on the supporting wall. Now think about it. This creates this involves many interesting situations. It might happen that the crack could close something like this, right? So you have a supporting wall, and let's say this part is fixed, and here is a crack, right? So it might happen that this node of the crack may meet before the bottom node, right? So that's what this set is saying. Like when the crack closes, it may happen that you may have this sort of situation, right? So it may be possible that there is a gap, right, when the crack closes, and then when it bounces back again, crack opens up. So many interesting situations are part of this particular set, right? Now this is how we model the unilateral boundary condition. All right, so sorry, I haven't used Zoom, so I don't really, I have little hard time to navigate this, but I'll try my best. Okay, so here is set J, right? This is the set in which we are trying to find out the solution for a dynamic problem, right? And this is how it's going to work. The displacement is going to be in a Sobolev space where U is 0 for every U belongs to this set S, right? So whenever the displacement will be considered as a 0 displacement, meaning that it will not penetrate the wall. Wall is the end, right? That is considered as a 0 distance for this node, right? The displacement is positive whenever U is outside this set S, but still in the domain, right? So if u is inside omega minus s, then displacement is positive, and that is really going to give us the opening of the crack, right? So numerically, this boundary condition is very important because that is something that we are going to use to model this crack. As I said, at the first guess, it looks like this is highly nonlinear problem, but this looking at this boundary condition should give you a feeling that there is some kind of linearity there, right? So this is the boundary condition, as I said, is used to create that artificial crack at the supporting wall. All right. So any displacement u in set J, I'm going to call it admissible displacement. This is the possible set of the solution, right? Possible displacement. Now, as I said, we have used these standard principles, right, to solve this particular problem. The principle we have used here is Hamilton's least action principle, right? It is really a very simple principle. It says that when you apply a force on any object, it is going to take a shape that minimizes the potential energy, total potential energy of the system, right? So this is the formula that this is the principle that I have used here. What that principle says, under that principle, I'm going to consider this particular problem. It says, find displacement u in the admissible set J such that potential energy at u is less than or equal to potential energy at point V for any point V, for any displacement V coming from the admissible set. So as I said, this is really the mathematical version of Hamilton's least action principle, right? Now, simple but tedious work convert this inequality into a very nice integral equation form, right? So we can get the following inequality using this top expression: find admissible deformation u for which for such that for all admissible v we have this inequality satisfied. Half of integral over the domain of this product involving partial derivatives. As you see, we have a difference of okay, so let me see if I can get rid of this this marks.
Dr. Jigar, you can use annotation, and that is a eraser.
Right, I was using annotation to draw it. Okay, great.
Yeah, now it is gone.
Yeah, we are using Teams here and e-learning Collaborate. So yeah, perfect. All right, so this is the inequality that can be obtained easily using this minimization problem. As I said, we are looking for the admissible deformation u that satisfy this integral equation, right? That obviously satisfy the contact boundary condition and initial conditions, right? So since the initial load is known, there is some initial shape, and then we have designed the boundary condition, so boundary condition will also help that. Okay, now to convert the problem into dynamic problem, we need to replace the force by the initial force, right? So f of tx is replaced by negative rho times second order partial derivative of u with respect to time, right? And again, that is really the standard setup to convert static into dynamic problem. So our inequality takes the following form. And again, this is the problem that we are trying to solve. We are trying to find out the minimum displacement from that admissible set, right, which satisfy our integral equation, right? And here is that integral equation, right? So obviously, I'm not going to read out that equation, but this is the same equation that we consider in the previous slide. I just replaced that force by this inertial forces, right? Okay, now the next part is to make this equation looks little better, right? So okay, so looks like I have the same slide twice. Okay, so now it's time to do the discretization, right? So we know this particular equation that represent the dynamical response of the cantilever beam under applied force. We also know how we design the crack in terms of boundary condition, right? Now it's time to do some numerical work, right? So how to make this work? As I said, up until now, analytic solution is completely unknown for this particular situation with given boundary condition. So this is what we have done. I really discretize one by one two things, right? The first discretization is a discretization of variable u itself. All right. So variable u, it has three components: x1, x2, and x3. Where x1 is related to the height, x2 is related to the length, and x3 is related to the width. Right. So length and width, it's not gonna change. Right. So what I did is we can restrict the degree of freedom of the system by assuming that the displacement takes the following type of form, right? U can be seen as a summation n running from 1 to capital N, Wn of t comma x1 times phi to the power n of x2 comma x3. Now think about it. What is this? This phi to the n times x2, x3. It could be some finite element scheme, or it could be mode of vibration, or it could be like some interpolation function, right? So this is something that is already known to us. What we are saying is, in order to find that admissible u, our goal is to come up with this Wn of t comma x1, right? Now, what is that portion represent? It really represent movement of the node that are attached to the supporting wall, right? So the node on the supporting wall are going to give me crack opening and crack closing. The other points on the beam, they are going to work according to those points, right? So if I know the movement of all the points that are glued, that are connected, let me use the word connected to the supporting wall when the crack is closed, of course, then that t comma x1, Wn of t comma x1, it really represent the location of all those node at any time t, right? All right, so that's how we do the space variable discretization. So as you see, two variables have been removed, because this is like completely up to us how we make a selection of these two other variables, right? Our job is really to find out the location of the nodes sitting on the how to say, on the height, right? So height means that the height has, there are few nodes that are fixed, they are not going to move, and there are some points that are loose. They represent crack opening and crack closing, right? So obviously we really would like to focus on those nodes only, and the remaining nodes, we are saying that it can be handled using some sort of finite element scheme, or you can use the vibration modes of vibrations, right? So if we do that, the same inequality can be converted into this particular form. This form looks a lot better than the previous one. It does not involve those partial derivatives, right? So you may wonder that where did they go, right? So they are still there. I really rewrite that particular inequality in this form so that it looks little better. Now you see some new things in here. There are three things here: a of x1, b of x1, and r of x1. And this a, b, and r, they store the information about those second order partial derivatives, right? So those integrals, right? So here are those three matrices. I mean, we can call it matrices. As I said, we started doing discretization already, right? So r of x1, it is this double integral, right? Ax1 is this integral. And as you see, we are integrating this interpolation function with sigma, with that tensor product. So this is really computationally possible, right? Because we are the one who decide what phi functions are, right? So this interpolation functions are known, or finite element scheme is known. So these integrals, they are computable easily, all right? If we do the time variable discretization, right? So we already did the space variable discretization. There is still second order partial derivative with respect to time left, that is coming from that dynamic, that inertial force part, right? So this inertial force part, that also needs to be discretized. And we are going to discretize this using the finite difference methods, right? So second order partial derivatives can be replaced by second order finite differences, right? If you do that, then the same inequality can be seen in little better form. And here is that little better form. V minus W transpose times MW plus B greater than equal to 0. Now, again, there are some new things here. M is a new thing. B is also a new thing. So M is really R plus K square times A plus B, right? So this new variables that shows up in the picture, they are something that we can compute, in other words, right? So, and B is R times W at T minus K minus 2 times W at T. Right now, remember, what was W? W is the part of that displacement, that particular admissible part that we are trying to find out, right? So as we replace that second order partial derivative of inertial force by differences, this is what we get. It simply says that, if you want to find out the next location of W, it depends on the previous location of the W and the current location of the W, right? So current location and previous location of that W is going to decide where your beam would be, right? So again, this is really like a very simple and straightforward formulation. As I said, those equation look scary, but trust me, computationally, it's not that bad, right? So this is the problem we would like to solve for any admissible V. We would like to find out W, which satisfy this inequality, right? And that W automatically will minimize the potential energy, because this is coming from that Hamilton's principle, right? And meaning that the solution that we found can be claimed as a minimum solution, right? And it's optimum solution. In other words, uniqueness is kind of automatic there. All right, so now let me talk a little bit about the computation and discretization that I did there. So here, for simplicity, I consider two-dimensional beam, right? So you can really think of this as, you cut the beam. You consider a cross section of a beam, vertical cross section of a beam, and it is always two-dimensional, right? So there are two things here, length and height, right? And as you see, there is a crack right there. I really put that dotted line to represent crack. So this point set, they are divided into three different sets, right? There is this set J1. That set J1 contains all those points that are literally connected, glued to the wall. They are not going to move, right? No matter how much force you are going to apply, these points are going to stay there, right? Then there are points that are not glued to the wall, right? These are the points that are going to lead to crack opening and closing as the beam vibrates up and down, right? And then this J3 represent all those nodes that are not a part of J1 and J2, right? So this is the picture of the discretized beam, right? And this is how we have used those conditions, right? So for the ideal beam, obviously, we wanted to compare the vibration of ideal beam with the crack beam. So I consider the similar system for ideal beam. For ideal beam, this is how that system looks like. We want M times W plus B at K to be free whenever K is in J1, right? So when the nodes are glued to the wall, so again, I use J1 and J2. Sorry, I did not put a picture there, but you can assume that you have ideal beam here with no crack, right? So I divide this point set into two sets, right? The points that are glued to the wall, completely attached to the wall, and the nodes that are, not a part of the points that are connected with the wall, right? So here is how the Hamilton's least action principle look like for the ideal beam, where there is no crack, right? All the nodes that are part of the set J1, they are free. Free means no matter what load you are going to apply, it is going to, stay there. It will not move. M times W plus B at K equal to 0 whenever K is in J2. So that means if the load, if the point is, if the node is a part of the beam, not a part of those fixed node, then it will try to minimize this potential energy. So it will try to, make this entry 0, right? The same thing is designed for crack beam. And this is how that problem looks like, right? Pretty similar, but slightly more interesting, right? For set J1 and J3, we have the same condition, right? J1 again represent the fixed node, right? They are free under whatever load, they are going to stay at their own position, right? For all those nodes that are part of J3, meaning not a part of the crack, right? These nodes, they will try to use the Hamilton's least action principle, right? Now, what is interesting are the next two lines that is giving us the crack opening and closing, right? And this is really two conditions, right? Condition number 1, MW plus B at K is going to be positive or 0 whenever K is in J2 and WK is 0, all right? So if WK itself is 0, right? Imagine the next WK plus 1, right? It's going to, be greater than or equal to 0, meaning, the crack is either closed or there is a gap, right? And then MW plus B at K is 0 whenever WK is already positive. When the crack is open, it will try to minimize the total energy, right? Potential energy. All right. So as I said, this last two lines, they are related to, this unilateral type boundary condition. It is, you can consider this as a discretization of unilateral type contact boundary condition that, when the crack is completely closed, this node has nowhere else to go. When the crack is completely open, the location of the node could be anywhere, but it will try to minimize the potential energy in some sense, right? Okay, so for ideal beam, solving this problem was pretty simple, right? You can solve this problem for WK by simply shifting B on the other side. M is a positive definite matrix. Things are very nice in case of ideal beam, right? As I said, analytic solution is known. So computationally, there is no challenge, right? The beam with the crack, however, gives us the following situation. And this problem is very well-known problem. This problem is called linear complementarity problem, right? And this is the problem that is satisfied at the crack location. Now, let's try to understand what does this try to say. It says B plus MW is going to take some value P, right, with W positive and P positive. And then we want W and P to be orthogonal to each other, right? So as I said, this particular problem is known as linear complementarity problem. And in order to have this solution of the dynamical system, we want this problem to be satisfied at the crack location, right? What we did here is we use a modified simplex method to solve this problem, right? The idea is simple, but it's kind of long. I really did this whole thing in that paper that I mentioned earlier, right? So this is what basically was done there. Similarity transformation was used to convert this matrix M into a matrix with all diagonal entries 1. Right, and then modified simplex method was used to solve associated linear complementarity problem, right? Those of you who are interested in it, I recommend you to check that paper. Very simple and straightforward idea was used there. Since we have like limited time, I really wanted to show you some results that I got there and perhaps the simulation if possible, right? So here are some results associated with this study. I use the following parameter to create the simulation, right? Length of the beam was considered as 12 meters. Thickness was 2.2 meter. I used LAM parameter, lambda equal to 1, mu 0.5. Density, I consider it as 0.1. Damping factor, I set it at 0.002. And I apply 1000 unit of initial force at the end of the beam, at the free end of the beam, right? This is how a picture of two beams looks like. The first picture represents the ideal beam. The second picture represents the moment of crack beam, right? Under the same applied load. I apply 1000 unit load at the free end on both beams. As you see, ideal beam, you can see clearly from the deflection that it's going to attain the value at most. It looks like close to -1, right? And this is way below -1. Crack is completely open, right? And as I said, no non-linearity is used, right? So this is really like a simple formulation of boundary condition leads us to this interesting situation, right? All right, so these are time step versus displacement graph. So if you consider like more vibrations, this is how both beams vibrate, right? So they don't look similar to each other, but however, if you see this, the scaling is less here. Here it's a little more, right? So this is less than -0.1. This is already more than -0.1, right? So this is really, in reality, this is a crack beam vibrations plot. So not sure why I did not scale it properly. But anyways, this is really the time step versus displacement graph. Here is one more plot that I have, right? This is same beam. I use the different set of, vertical and horizontal node to run the simulation. Picture shows you how complete opening of the crack looks like, right? Now let me show you how this simulation looks like. I created a short video for, beam vibration for 1000 unit force for a crack beam and for ideal beam. And you will be able to clearly see how nicely the crack opens and closes under the applied force. And so the first video represent ideal beam vibration. Okay, does anybody know how to run a video? I know that this runs with my laptop, but for whatever reason, it's not. Okay, so there is an AVI file.
Dr. Jigar, you can use control click.
Control click.
If it works. And I hope both your files are in the same folder.
They are in the same folder. Yes.
Then control click may work.
It's not doing anything. Yeah, I'm using Mac, and this is AVI file, so that
then it won't work. Then it won't work.
Okay.
It is not compatible with this.
Okay.
No
I can send you this two short videos. Maybe you can include it somewhere.
Yeah, sure. I will do that.
So, all right. So again, this was like interesting part that I really wanted to show you guys, because you really would like to, after seeing all this theory, you really would like to see that how really this whole thing happens in terms of its simulation. Now, there is one more interesting thing here. As I said, I earlier mentioned that when the crack closes, right, these nodes sitting on the crack tip, they are hitting the wall with non-zero velocity, right? And there is some kind of energy dissipation, right? So the question is like, is it possible to see the effect of this hitting? So I try to, plot this movement of the node sitting on the crack tip. These are the pictures taken from the beam, discretized beam with crack length 6, right? So there are 6 nodes sitting on the crack tip itself, and then 5 other nodes, right? The first picture in the bottom, right bottom, it represents the movement of the node on the crack tip itself. The crack tip itself is not moving. You see the flat line there, right? The node next to the crack tip, it has some movement, right? So it has this this bumpy parts, and then there is this like some noise kind of thing. I believe that noise kind of thing, it's due to the impact, right? And this model can be used to study the impact, to do the impact analysis as well, right? The first picture in the second row represent how the movement of the third node from the crack tip, right? And then obviously the first one, it shows up, the movement of the top node on the crack tip, the very first node from the crack tip, the very first node on the crack itself, right? And as you see, there is this noise part. I believe it is due to the impact that happens, and energy dissipation happens because of this. There are some open problems that are related to this thing, right? So as I said, the first thing, obviously, impact part is something that we are working on, and shortly, I'm in process of writing a paper on this impact part. Comparison between crack beam vibration and ideal beam vibration. This is going to give us some useful information, right? So, for example, let's say you are flying in the plane, right? So it's a brand new plane we already know how it, if we, under normal circumstances, let's say we have a data for its wings vibration, right? Now, suppose this wing develops a crack, right? Then vibration would be different, right? One thing that we could do is we can think about this active vibration control, right? Like when plane is flying in the air, right? Due to the turbulence, sometimes the wing flatters very fast, right? So is there any way that we can, stop this vibration, make it to the rest, so that we can, I'm pretty sure that they have all kind of mechanism, but, identifying the crack location is one more interesting question. This is really the inverse problem of what I did, which is technically slightly more rigorous. As I said, control can be designed, right? So control design for ideal beam obviously is not going to work for crack beam, right? So if you design some sort of a control mechanism to stop the vibration for ideal beam, if there is a crack in the structure, that same control, it's not going to work. So is it possible to design some sort of a smart control using this piezoelectric or any other type of fancy material that may help reducing the vibration and save the entire structure? So these are the things that are still in progress. How adaptive control work in case of multiple cracks. Now, in this case, I completely ignore this crack propagation issue, but this is really a real issue, right? Like when you apply the force, if the applied force is more, then you may have a catastrophic failure of the entire structure, right? The system breakdowns, right? So for this particular study, I only apply the suitable amount of force so that I get a full crack opening and closing, right? I did not apply any random kind of force. Random kind of force, again, it may lead to crack propagation or permanent failure of the system, right? Okay, so that is pretty much it. Looks like I take like 5-10 minutes more, but I'm really sorry for that. If you have any question, feel free to, I will be more than happy to answer them. And again, I would like to thank you all for giving me an opportunity to give a talk among all the respected faculties with whom I studied there. You have a great contribution in my academic career. And my teaching is completely influenced by all of you. So thank you so much for giving me an opportunity to present myself here. And all students who were part of my batch, I really would like to thank you too to attend this talk.
Thank you, Dr. Jigar Patel, for a very informative and realistic situation of crack and how one can handle it, how it works and how one can handle it. In India, we really have this issue very seriously, almost everywhere. And students who are actually live on YouTube, okay, this lecture was live on YouTube. So students are on YouTube.
Ah, okay, I see. Nice.
Yeah. So thank you very much. And I hope some of the students will like to go for doing some work in solving a crack problem, because it is, in fact, multidisciplinary. One should have physics knowledge, one should have math knowledge, and at last, optimization goes on, because you wanted to have the minimum deflection and minimum crack opening could be good enough, but it has to be in the minimized stage when certain amount of force is applied.
Right.
Okay. So thanks once again. And we are proud you to be alumni of Department of Mathematics.
Thank you.
So thank you. Thank you.
Thank you, Jigar. Thank you.
Sir,
Congratulations.
thank you.
Nice, wonderful talk.
Thank you.
Recording stopped.
So thank you, Jigar. And we are sorry that we had to ask you to stay with us till late night. Okay.
No worries, no worries.
So thank you. We can end the meeting here. And thank you, everybody, those who attended virtually on Zoom platform and those who are on the YouTube. Okay, bye-bye.
Bye.
Bye. Thank you.